Hello students, now in this video let us see how to solve non-homogeneous linear recurrence relation. So first of all let us see the definition. Non-homogeneous linear recurrence relation. Consider a linear recurrence relation with constant coefficients. Okay, let it be C0 AR plus C1 AR minus 1 plus C2 AR minus 2 so on up to C AR minus K is equal to F of R. Okay, let it be equation 1 where C0, C1, C2 so on up to Ck are non-zero real constants. Non-real constants. Now here if f of r is not equal to 0 in equation 1, then it is known as non-homogeneous recurrence relation. Non-homogeneous recurrence relation. Okay, now solution of such a recurrence relation has two parts. That one part is a homogeneous solution, which is the solution of associated homogeneous part of the equation, and second part is the particular solution which satisfies when f of r is what? Non-zero. So what can we say? The solution of one has two parts. One, how does it? Where f of r is what? Non-zero. Already we have seen when f of r is the homogeneous recurrence relation. In previous videos we have solved that one. Now this has two parts. So first one, homogeneous solution. You know this one, homogeneous solution is a solution of associated homogeneous part of one, and the second part is what? A particular solution. Now what does this? Which satisfies equation 1 when f of r is not equal to what? 0. Now from that we get one more new definition, that is what? A total solution. or it is also named as, this is also what, general solution. General solution or total solution, so you can say. Now what does this? Now here, this homogeneous solution is denoted by ARH, while this particular solution is denoted by what? ARP. This one. These are the notations. So this total solution, what does this? Here, let its definition of total solution. So let ARH and ARP denotes homogeneous solution, homogeneous solution and particular solution. The first one denote the homogeneous solution and second one denote the particular solution respectively. Then the general or what can we say, total, general or total solution is the sum of these two solutions. These two solutions, which is given as what does that? We can say general solution. General solution is what? ARH plus ARP. This is an important thing. You should remember this. Whenever f of r is non-zero, means a non-homogeneous recurrence relation is there. That time always we need to find this homogeneous solution as well as the particular solution, and we will add them to find what? The general solution or the total solution. This is very important here in case of non-homogeneous linear recurrence relation, that is f of r is not equal to 0. Now we had already seen about how to obtain homogeneous solution. Now the question is left for how to find a particular solution. So let us see. Actually, like the homogeneous solution, there are no general steps to determine the particular solution or to finding the particular solution, but it depends upon the nature of function f of r. How does that function will be? Means either it may be constant, it may be some linear value, it may be quadratic, it will be a polynomial. What is its order and degree and all. Now let us see some functions having a particular solution is given. So now we will see some of them and see how does the characteristic root of them, according to we can write the particular solution for them. So let us see that one chart. Now here we will see a list of forms of particular solution for a certain kind of f of r. So let me prepare a table here, a rule, or it will be simply a serial number. Suppose rule 1. Suppose f of r is constant. F of r is what? Constant. It is a constant function. Constant means just a number, just like a 2, 3 as such. Now here it will be a constant and characteristic root is about characteristic function characteristic equation. It is a root of characteristic equation. In that one, suppose alpha equal to 1 is not a characteristic root. Characteristic root means f of r is some constant function. A condition on characteristic root that alpha equal to 1 is not a characteristic root. In that case, how does the particular solution? It will be simply some constant p in that case. Then second rule says f of r is some constant and here alpha equal to 1 is a characteristic root. Is a characteristic root of multiplicity. Multiplicity means what? It occurs m times. Suppose it occurs twice, we will say m is equal to 2. Multiplicity is 2. If it will occur times, then multiplicity will be 3. Okay. So now here, let me prepare this one. If it is bad, I will increase that. Now here, this is 1. Now rule 2, we are seeing this f of r is constant, but alpha equal to 1 is a characteristic root of multiplicity m. In that case, the particular solution will be p r raised to m. As such, we will write that one. This is the rule. So now, third rule says f of r, suppose of this kind, c lambda raised to r, where this lambda is not characteristic root. This lambda is not a characteristic root. In that case, this particular solution will be p lambda raised to r. Simply it will be p lambda raised to r. Now fourth rule, f of r is again c lambda raised to r, while now lambda is a characteristic root. Lambda is a characteristic root of multiplicity m. In that case, the particular solution will be p lambda raised to r into r raised to m. Then fifth rule says, suppose f of r is polynomial, will be as such: b0 plus b1r plus b2 r square plus so on up to bm r raised to m, where alpha equal to 1 is not a characteristic root. Is not a characteristic root. It is not a characteristic root. That time, simply these bi's are replaced by new constant, that will be our particular solution. p0 plus p1r plus p2 r square plus so on up to pm r raised to m. This is the fifth rule. Now, sixth one, f of r is of same kind, just like in fifth. b0 plus b1r plus b2 r square plus 1 up to pm r raised to m. But now alpha equal to 1 is a characteristic root, is a characteristic root of multiplicity m. of multiplicity m. This is the way. So now here, what will be the particular solution? Particular solution will be P0 P1R plus P2 R square plus 1 up to Pm R raised to m into R raised to m. Okay. Then next one, suppose f of r is B0 plus B1R plus B2R square plus up to Bm R raised to m into lambda raised to r, and lambda is not a characteristic root. Lambda is not a characteristic root. Therefore, particular solution is P0 plus P1R plus P2R square plus 1 up to Pm raised to m into lambda raised to r. And last rule give here f of r equal here, this is equal to f of r equal to br plus b r square plus so on up to bm r raised to m into what? Lambda raised to r, where lambda is a characteristic root of multiplicity m. Lambda is a characteristic root of multiplicity m. So, what will be particular solution in that case? The particular solution will be 0 plus P1 plus P2R square plus so on up to Pm R raised to m into lambda raised to r into r raised to m. These are the rules for some types of functions. If any one of these f of r will come with these conditions, then we can write the particular solution as such. These are the ways to write the particular solution for those one. Now, we will see some examples for these so that you can easily remember them. So now, let me take a small example. Hopes you all understand this. Now, let us see the example so that you can easily remember this. Example: find the general form of the particular solution of the recurrence relation AR minus 18 AR minus 2 plus 81 AR minus 4 equal to f of r, where f of r is equal to Now the first one is 3, second one 2 plus 3r, third one 2 plus 3r plus 3r square, fourth one r, fifth one 3 raised to r, next sixth one r 3 raised to r, and one more. It will be r square minus 9 into 3 raised to. As such, for this each and every one we have to find a general form of particular solution. Now the solution. Now to find the general form of particular solution, first of all we need to obtain the characteristic roots. So for that, the characteristic equation of given recurrence relation is what does that? Now here it will be 4, k will be 4, so alpha raised to 4, but this is alpha square, this is alpha raised to 0, so it will be alpha raised to 4 minus 18 alpha square plus 81 equal to what? 0. And if you carefully observe here, this is nothing but alpha square minus 9 whole square equal to 0. So alpha minus 9 whole square equal to 0. So that is alpha square minus 9 equal to 0 twice. Alpha square equal to 9 means plus minus 3. So here the characteristic roots are plus minus 3 we will get, but this characteristic roots are 3, 3, minus 3, minus 3. 3 times 3 twice and minus 3 also twice. Here it will be 3, 3, minus 3 and minus 3. Now once we get the characteristic root, using that previous table we can easily write the general form of for these f of r, general form of particular solution for these f of r. So let me solve the first. What is f of r is what? 3. It is what? Constant. It is constant, and is not a characteristic root. 1 is not a characteristic root. Okay, so this gives, by rule 1 we can see here, what is the particular solution is simply P. Now second one, f of r what? 2 plus 3r. It is like 0 b1 r, 0 plus b1 r, so it is a polynomial degree 1, and 1 is not a characteristic root, is a polynomial of degree 1, and 1 is not a characteristic root. So this implies here what is the particular solution? It will be P0 plus P1R simply. Next, f of r is 2 plus 3r plus 3r is also a polynomial of degree 2. Polynomial of degree 2. 1 is not a characteristic root. 1 is not a characteristic root. So here also it is a particular solution is P0 P1R plus P2R square. Next one, f of r over r is a polynomial. The polynomial of degree 1, and 1 is not a characteristic root. So here also particular solution is P0 plus P1R. Next one, f of r is what? 3 raised to 3 is a characteristic root. It is of the kind lambda raised to 3 is a characteristic root. That lambda is a characteristic root. Of multiplicity 2. Now 3 occurs twice the root in characteristic root. So its multiplicity is what? 2. With multiplicity 2. Therefore, this gives our particular solution using that rule of lambda raised to r, for lambda is a characteristic root with multiplicity m. So our particular solution is P r square 3 raised to r. Next, f of r is what? r 3 raised to r. So it is a polynomial into lambda raised to r. Again, lambda is what? A characteristic root. Characteristic root of multiplicity . So here by rule 8, last rule is this. So here particular solution will be what? P0 plus PR, as it is a polynomial of degree 1. So that's why such linear or the polynomial of degree will occur there with the different constant into r square 3 raised to r. F of r is what? R square minus 9 3 raised to r. Again, this is quadratic polynomial into lambda raised to r. So with 3 is, this lambda is a characteristic root. Lambda is a characteristic root of multiplicity 2. Of multiplicity 2. Okay. Therefore, again by rule 8, here also particular solution will be P0 plus P1R plus P2R square into R square raised to R. As such, the general form of particular solution for the various of R's we can write. Okay, so now here we will stop for this video. In next video, we will see some more examples for finding the general solution, not only particular solution, but the general solution. Okay.